Hey everybody, when you come in, go ahead and I'd love for you to answer the poll that's here. So we're just checking to see which AP Physics 1 test administration are you going to take? Is that going to be May the 5th, which is Wednesday, May the 24th, which is the second administration, and that's a Monday, or are you going to do the digital one, which is June the 9th? So we'd love for you to go ahead and hop on to that and let us know what you're going to do, if you're going to do May 5th, May 24th, or June 9th. The other thing that you could do is in the chat, I did put a link to the pair deck that we're going to do today. And if you can get onto that pair deck, that would be awesome. Pair deck is just a great way for us to be able to interact. That way I can kind of see what you're thinking and what kind of answers you have and what you know. That helps me as we go through this to make it tailored to you just a little bit better. And so hopefully you'll do that for us. That would be awesome. And then if you don't mind doing the poll is just a little informal poll, doesn't mean anything other than we just kind of want to see when you are taking the exam. So we've got 3 students so far on the pair deck, and we have 4 o'clock right on the dot. So what we'll do is we'll just keep putting that we'll just keep putting that into the chat. If you don't mind, we'll give you another minute or so. We're going to start at about 2 after the hour, so 2 after 4 o'clock Eastern time, just to give you a little bit of time to get in and go ahead and vote on the poll, and to also go ahead and get into the pair deck. So we've got 5 students so far on the pair deck, which is fantastic because I think you'll get some great stuff from that. At the end, we'll also make sure that you have the link to the takeaways. Takeaways for pair deck are just Google Docs. They show the whole Google presentation that you get. So this is done in slides, and then we use pair deck to make sure we can kind of see what your thinking is. And then after you do that, you'll get a link and you'll be able to go in and check it out on Google Doc. So we've got about 30 more seconds, and I'm going to end the poll here in about 15 seconds. You can kind of see where everybody who is here is at in terms of what they're going to do. And so here we go. This is what everybody's doing so far. And it looks like about out of the 4 people that voted, 3 of you are doing the version on May the 5th. 1 person's doing it on May 24th, and June 9, we don't have anybody at all, which is good. The digital only version is going to be pretty tough. It is one where you have lots of multiple choice, and you can only look at one multiple choice at a time. And once you answer it, you cannot go back. So that one's going to be kind of a tricky one, I think. So we'll see how that goes. All right, so I will keep putting in the chat the pair deck link so that you can kind of see it. And we're going to go ahead and get started with this. So welcome to Fiveable's AP Physics CRAM review. This one is on Simple Harmonic Motion. Don't forget, this stream is being recorded and might appear on our website, YouTube, or other public channels. So if you ask a question, your name may appear on the screen. Please make sure that if you don't want your name to come up as your name, you change it. As always, if you like what you see, let us know all about it. So go onto Twitter, say, hey, you know, have been having some awesome sessions in all kinds of different AP courses. And do that in Twitter. You can do that in Instagram, or do that in YouTube. Any of those are going to be fine. This next week, we're going to have Unit 7. So that'll be on torque and rotational motion. That is on the 15th at 7 p.m. Eastern time. The week after, we'll have some AP Physics 1 free response tips and tricks. That'll be on experimental design and short answer. And then we will have another one for free response tips and tricks, but that one will focus really more on QQT, qualitative quantitative translation, and paragraph length response. And that one will be at 6 p.m. on the 28th. So lots of streams coming up, getting you ready for this big exam that is coming up. So today we're going to take a look at what is simple harmonic motion. We'll go through some graphs. We're going to do a lot with horizontal and vertical springs. And we'll also talk a little bit about pendulums and how they are swingy things. So hopefully that'll be super helpful for everybody so that you can strive for that 5. When we take a look, I'm going to get rid of the poll here. And there we go. So when we get in, notice that periodic motion is anything that describes motion that repeats over and over. So we can think about uniform circular motion or simple harmonic motion. Orbits, whether they are circular or elliptical, are also periodic motion. So we could also think of some others, like if I have a puck on an air hockey table and it bounces back and forth but never loses energy, it just kind of keeps going forever, that would be a good example of periodic motion. If a golf ball bounces up and down and never loses energy, that would also be periodic motion. If we think about simple harmonic motion, or if we think about just periodic motion in one dimension, there's a location that we have called equilibrium, and that's where the object doesn't experience any force. The other thing that we need to know in order for something to have periodic motion is there has to be a net force acting on that, and it is always directed towards equilibrium. So if you think about a spring, you can compress it or you can stretch it, and then the point in between is what we call equilibrium. So simple harmonic motion is simple because it is a periodic motion that is the simplest to model using math. And if the object exhibits simple harmonic motion, then the following 3 properties have to be true. If one of the properties is true, then they're all true together. And if one is false, they're all false together. And that object then exhibits simple harmonic motion. The net force, this is the first one, the net force on the object is directly proportional to the object's displacement from equilibrium. So if the force goes up, then the displacement goes up. If the force goes down, the displacement goes down. The object's motion, number 2, can be modeled as a single sine or cosine graph. And so we'll take a look at some of those here. In fact, we're going to take a look at a lot of them. And the period of motion is independent of the amplitude. So it doesn't matter how far you stretch a string or how far you pull back a pendulum to a certain extent. In AP Physics 1, it won't matter. So when we look at amplitude, amplitude isn't going to matter at all. A spring and mass does meet all 3 of the criteria. So you'll see here the force position time is a nice straight line. So that tells us that the spring exerts a force that is directly proportional to the displacement. If we look at the graph, we see that it is a nice sine or cosine function. And here the amplitude makes absolutely no difference at all. If we look at a pendulum, it does meet all 3 criteria, but we have to be careful because this pendulum can't swing any more than 30 degrees from the vertical. So for a pendulum, that force and angle here up to that 30 degrees will work really well. After that, it just doesn't. The position versus time for amplitudes of less than 30 degrees, we do have a sine or a cosine, otherwise it kind of breaks down. And then the period versus amplitude, the amplitude really doesn't matter, but remember, we're trying to keep those amplitudes really small as we go through. If you have just joined us and you want to jump into the Pear Deck, I've put the Pear Deck link into the chat so that you can hop on and take a look at that. So a bouncing golf ball, let's think about it. It does not meet any of the criteria because it is not simple harmonic motion. The force on the ball is huge when it hits the ground. So that's what happens here at the beginning. And then a constant mg when the ball is in the air. So hits the ground, then it's in the air, then it hits the ground, then it's in the air. And you'll notice that this is not a sine or a cosine graph. You'll also notice that the period definitely depends on the amplitude. If you drop it from a low height, it bounces a whole bunch. If you drop it from a higher height, it bounces less often. So bouncing balls, even though they're periodic, they are not simple harmonic motion. Equations that you'll see on the equation sheet, these are the big three that you're going to need to make sure you know how to use. Remember, they are all on the AP Physics 1 equation sheet, and these are somewhat in a similar area, left to right on the equation sheet. So we've got our first one for a spring where m is mass, k is the spring constant. Pendulum, we have L for length of the pendulum and g for the acceleration due to gravity. And then this one is one that we're going to talk about here next, and this is for the position of an object in simple harmonic motion. And we're thinking about the position on a position versus time graph for this. So this is this weird equation that not a lot of teachers and not a lot of students pay attention to, but it's a part of the test every single year. And if you know how to use it, it's pretty easy free point. So here's how we read this thing. Whatever the number is that we have outside of the cosine, so you'll have a number here typically, that's just the amplitude. Whatever number is inside with the t is equal to 2 pi f, and that is f for frequency. So for example, let's say that I have an oscillation and it is 3 cosine of 10 times pi times t. The amplitude for this thing is 3 meters. So if I took a slinky and I put a mass on it and I took it into a really big area, so for example, maybe over the balcony of a gym, or if you are able to get into some other really high ceiling area like an auditorium, the amplitude would be about 3 meters. The frequency is 5 hertz, and that's because if I take 10 times pi, and that's equal to 2 pi f, my frequency would be 5. The period then would be 0.2 seconds, since period is equal to 1 over that frequency. And if I insert a time of 3 seconds into this equation, then I get 3 cosine of 10 pi times 3, and that position would be negative 0.222. So that's how we use the equation. It's a little different than a lot of the other equations we use, mainly because of the cosine function. This is where we're going to start working together. So we have a block. So you'll notice here's the block. It's hanging from a spring. We're going to pull it down to C, and that is a small distance from the equilibrium position. So that would be our amplitude. And we're going to let go of it at time is equal to t0. So the period of the resulting simple harmonic motion is t. That means that one cycle will be over when it hits t. And so then a second cycle will happen when it hits 2t. I would love for you to try to sketch a graph of position versus period for this block spring system. We're going to let the vector quantities be positive for the upward direction. So when it travels upward, you're going to want to make sure that that for this position versus time, that your springy thing is also, your graph is also moving upward. So looking good so far. So Giesel, good job. Excellent, excellent, excellent. That looks really great. Grace got a little start there. That's nice. Anybody else that wants to jump on, go ahead and jump on. Remember, don't worry if your solution is incorrect or correct. We're not going to worry about that. We're going to just go through and take a look at what you're doing. And as we go through, I think these will get easier, but these are some of the ones that are the more difficult ones to do on the AP test. Simple harmonic motion throws a lot of students, but after this, I think you should be 100% fine. So I'm seeing a lot of really great drawings here so far. So I love it. Excellent job. Very nice. And Anna, good. Rachel, very good. Josh, nice job. So we're seeing a lot of great things here. Rachel, excellent. Josh has got something drawn. So does Anna. Okay, good. Awesome. Okay, so I'm just going to show you some of these responses because I want you to see, and remember, your name is not tied to these. So when we look at these, you're going to see a lot of different curves. And that's really kind of what we want, because if you come into this and you get everything right, then I haven't really done much to help you out. So let's take a look at what some of you have done. So we have all kinds of graphs here. And you'll notice the orange one starts up top, comes down, comes back up, comes down, comes back up, comes down, goes back up. Here we've got one, and this one, these two are very, very similar. They both start below the line, and then they both then come up to a peak just a couple of blocks after that, and then come all the way back down. So the only difference between these two graphs is their amplitude, which is super cool. Same thing on these two. The only difference between the two here is their amplitude. I think this one and this one are very similar. Same thing, amplitude is the difference. So the answer to this one is the graph that you see in front of you. Now, let me explain to you why this one is the way it is. The block is pulled down a small distance from equilibrium. If you notice this T line, the T line is where equilibrium would be. If it's pulled down a little distance, you could go down as far as you want to, because we don't have any numbers here. This is called a qualitative graph. And sometimes they'll ask you just to sketch things. So this one does say sketch, which means you don't have to put any numbers on it at all. When you sketch this one, we started at the bottom, so I know that one cycle means I should end up where I started. So I know that I'm going to start here and I'm going to end here. In between, I need to hit letter B twice. So if I say letter C is down at the bottom, letter B is right in the middle, letter A is up at the top, I've gone up, I hit letter B, I go to letter A, I hit letter B on the way down, and then I'm down at the bottom at letter C again. So this is the response that we were looking for. We're going to do this same thing again, but this time we're going to go ahead and give you the position graph, and I want you to sketch what you think a velocity versus period for this block spring system would look like. So think about what is the slope of the position versus time graph. If you do that, you might end up with a little bit better picture than if you don't think about slope. The other thing is remember where the slope is really steep, you have a really high velocity. So both at this point and at this point, you have a really high slope. Oh, what task verb? It would be plot. So the task verb here is sketch, but when you need to use numbers, that would be plot. Excellent question. Very, very awesome question. So, and this person is talking about task verbs. Task verbs are found in the AP Physics 1 CED course and exam description. In that, it has a list of all the verbs. So if you come back when we talk about free response questions next week, not next week, but in 2 weeks and the week after, I have a list of all of those. And I think that'll be super helpful for you. All right, I am seeing some awesome things. Hey, Kayla, I love what you did there. So that's awesome. We will go through that so everybody can see it. Excellent job. All right, now we're getting more participants here, just kind of coming in and putting some awesome things in. Very good. Excellent job, guys. Perfect job. Awesome. Thank you very much. There is a list. Here is the list. You'll see it. It is in the chat. So if you pop that chat open, you'll be able to see that list. So thank you for doing that. I really appreciate it. So in the chat, you'll notice there is a list of those verbs. I'm going to pop it open here too, just so you can see. And these are AP Physics 1 exam tips, so thank you for doing that. Here are all of those task verbs. Excellent. I love it. All right, cool. Let's take a look at some of these graphs that you all have done. I'm going to put these in a grid layout, and we'll project them so you can see. Remember, your name will not be on here. But now we're seeing a lot more graphs that are very similar, so nice job on these graphs. Let's go through and take a look at what the correct answer is for this one. And you'll notice that it does start right at the origin. And the reason it starts at the origin is at this point, we don't have any velocity. At the very top, there's not any velocity. And somebody did a really good job of showing that. So I'm going to open up this one, and you'll see that this person has, at these different points, found out that the change in position over the change in time is 0. And because dy or dx, or however you want to do, if you're going to do calculus, that's absolutely great. This would be dx over dt, and that would be 0, 0, 0, 0. And so they went through and put their zeros in at each one of those spots. So very nice job. But that is definitely the answer. You'll notice that it is a complete wave, and then this is another complete wave. For the position versus time, this is a negative cosine graph. And the reason I know that is it starts below the 0 line, and that makes it cosine. If it starts above or below the 0 line, it's cosine. And because it's down below, we're going to say it's negative. This one is a sine graph, and because it goes up first, it is a positive sine graph. So a negative cosine and a positive sine. Very good. Let's take a look at the next one. This is acceleration. I'm going to give you a little hint about the acceleration versus time graph. It is the inverse of the position time graph. So you have the position time graph. If you flip that upside down, you will have the acceleration versus time graph. So hopefully that's helpful. Go ahead and try to draw the acceleration versus time graph, or acceleration versus period graph, based on the fact that it is the exact inverse of the position versus time graph. So I'm already seeing people do it. It is doing a great job with that. Good. So one person is, oh, they were almost done. Nice job. Gisel, good. Job, Josh. Way to do it. Excellent job. All right, very nice. Good job, Rachel. Okay, everybody's doing a fantastic job on this. Excellent. I love it. You guys are doing fantastic. I love how you start with dots. So a lot of people are starting with dots, and I love the fact that you're starting with dots. I'm going to even show you one here that's starting with dots. You can kind of see this person as they work, doing a really good job of making those dots. The hardest part then is putting the curve on it, and they did an awesome job of that too. So really, really, really good. So this one, as we know, is the inverse, and you'll notice that when this one starts low, this one's going to start high. They both are going to be at the equilibrium point at the same time, and then we just flip it. So the peak here is going to be a trough here. Excellent job. So let's go ahead and do the next one. Now, we can also plot momentum versus period. I gave you velocity versus period. Let's see if you can figure out what it would look like if it's momentum versus period. So we've got momentum. So remember, momentum is mass times velocity. So remember, momentum is mass times velocity. And I love the fact you're listening, because I watched somebody start it, and then they heard the equation and they started to change what they were doing. So I love that. Good job. So if you just remember, yeah, nice. Nice, Gisel, good. Excellent. Looking at your responses, they look really good. So remember, job, Spandan. Good, excellent. Now, if you want to add to this and you want to make it a little bit better, you could put a little bit more magnitude on the momentum graph. And the only reason we would put a little bit more magnitude on it, and this one looks really good, this one looks great. They should should look just like the velocity versus time graph. I did have one person did this, so this is really good because if the mass is big, then we see a bigger curve here. So the amplitude will grow. And so here this person did that, and that's awesome. So nice job, everybody. Good, good, good. Let's go ahead and do the next one. Well, here's our answer. So this one we didn't take into account the mass. We just kind of said, well, momentum and velocity are related, so we're not real worried about the values or the magnitudes. We're just trying to sketch them. This one is force. So what would the force versus time look like for this? And I put a little hint just above it for you. So we put just a little hint right above it. This is going to be the last of the easy ones. We're going to do a couple graphs that are going to be a little bit more difficult. Good job. I love the dots. Those of you going through and doing dots first, that is the way to do it. So you'll see this person did their dots. And once they get done with their dots, they're going to go in and put the curve in, which is what they're doing right now. Fantastic. Good job. And we have seen a lot of times where you'll need to do this. Yes, that would be correct. So somebody says the acceleration versus time graph for a simple harmonic oscillator is in the inverse of the position graph because of Hooke's law. So for a spring, that would be correct. If it's a pendulum, that's a little bit different. So it's mainly just thinking of F equals ma. I think that's your big thing that you want. All right, so really good responses on this one. You'll see we've got our first one here. We also have several others that look really good. So I'm going to unstar one answer so we can see the others. And these all should be very similar. Very, very, very good. Excellent. All right, so now it is time to stretch a little bit, no pun intended. Check this one out. We have position versus time, and now I want a graph of potential energy versus period. Potential energy versus period. So you'll want to think about what is the potential energy for this spring system. Excellent job. You were on it today. I love it. Giesel, good job. Excellent. And nobody has asked a question about this one yet. So let's see if somebody asks the question that I think might need to be asked here. I'm looking at your work. Looks good. I like it. Sauna, good. No, that's fine. It looks great. So it'll be interesting to see what everybody has here because this one does stump people. Do you need to know any value for K? You really don't need to know a value for K since you're just sketching. If you were plotting, absolutely you would need to know a value for K. All right, you guys are doing fantastic. I love it. Lots of different responses. I love it. Good, good, good. So I'm going to show you some of these responses, and then I'm going to make a comment. And let's say if you catch what's going on here. So for this one, if we're just thinking about spring potential energy, we get one graph. If we're thinking about spring potential plus gravitational potential, you're going to get something slightly different. So we're going to just stick here with the spring stuff. You'll notice that if we just think about spring, that there are a few of these that would be really good and a few that you'd have to modify. So when we think about spring potential energy and it's 1/2 kx squared, then we have to do the following. If I make x -1, but I square it, it's still +1. If I make it -2, it'd be +4. So you'll notice that the spring energy here would never be negative. Instead, we would always have these positive, we'd always have positive for our curves. So the correct answer for this one, if we're thinking about the potential energy of the spring, or we're thinking about the potential energy of the system stating that C is going to be our zero line. So if we make Z a C, our zero line, then we would come up with a graph that looks like this regardless of whether we're doing spring or gravitational potential. So that's the tough one on this one. So that is definitely the tough one. How about if we do kinetic energy? So we've got our velocity versus time graph. What would the kinetic energy versus period graph look like, or kinetic versus time and time period? They're kind of interchangeable as we go through. So what would our kinetic energy for the spring versus time look like? Excellent. Some of you have been really studying these, or you just got done with this unit, one of the two, and you remember what's going on. These are definitely AP level questions for the energies. These are things that they more likely would have you do. Go through and sketch these based on a graph that they've put above. We've seen them do this a lot. And then they might even have you explain. So I love what we've got some people that like to go in and give equations, and that would be the basic physics part. So that is phenomenal. Excellent. Good. Nice. Seeing some great responses here. I'm going to show you this one. This one, the person has put in the math to just kind of show what's happening here. And they're going to keep going because they're adding something to it. Excellent. So here we can see that the the kinetic energy is based on our velocity. So 1/2 mv squared. Our velocity, even though it's negative here, we square it. So we're going to have a positive kinetic energy. So they've done that all the way through. They've also treated this in a rotational motion fashion too. And so if you're taking AP Physics C, this would be a good way to go through and kind of look at how this is going to work. So excellent job on that. Nice, nice, excellent. Here's that same graph again. This is the correct solution. You'll notice that it does follow the velocity graph. And then instead of going down, you just have to flip it and invert it any time that it goes negative. You just leave it positive. So pretty easy to remember once you've seen it, but something that the College Board will do. They're not trying to trick you. They're just trying to see if you truly understand what's going on. So nice job. Last graph for this vertical spring. So I want you to plot the total energy versus time. Plot the total energy versus time. So that is the sum of all of the mechanical energies. We're going to assume that it is not losing any energy due to non-mechanical energies. So for example, we're not worried about friction. We're not worried about any heat being generated from friction. There's no chemical energy here. So there's no dissipated energy at all. And you guys are doing a fantastic job on this one. Excellent. Nice job, Anna. Job, Rachel. Job, Spandan. Critique, good job. Excellent. All right, we're getting the same thing. Looks like everybody's doing about the same thing, which is what we really like. So for this, you'll see that everybody has put a straight line for the most part. If you've put a straight line, I'm going to overlay these. You can kind of see those straight lines. Somebody's going in and putting in the U and the K. And so you can see how they kind of combine together in order to make that total energy the same. So nice job. That is fantastic. All righty. So there's the answer. You could have this at any point above the line. You wouldn't want to have it down below because your total energy should be positive as you go through. So nice job. Okay. Take a look at this one. This is a mass that is no longer, so we've taken our spring system and we've made it horizontal. I want to see if anything is different. So here is, here's kind of where you'll want to start. You'll notice that down on the bottom, you have B, C, B, A, B, C, B, A. You really just need to go from the first B to the third B. You don't really have to go any further than that for these graphs. If you want to go all the way across, you can. But what's happening is the mass is pulled left over to A. They want you to start your graph at B. Notice that it has a velocity at B, and that velocity is to the right. So when we pull it over and we let go, we're going to start graphing what this block is going to do, and we're going to start that graph at letter B. So when it's at B, we know that it has a positive velocity. So if you want to go ahead and put a dot right here, this would be your positive velocity. So this would be your positive velocity. So if you want to stick that right there, you sure can. We're going to say anything to the, it says consider point B to be the 0 position. Anything to the right is positive. Anything to the left of B is negative. So when you do that position versus time graph, be cognizant of that. Make sure that you understand point B is 0. Point C would be positive. Point A would be negative in terms of position. So seeing a lot of great responses so far. You guys are doing beautiful. Excellent job. And I see people are remembering that position and acceleration are inverse. And so Rachel, nice job on that. Excellent job. Excellent, excellent. And remember, you don't have to draw too many curves. If you just want to draw a single wave, that would be fine. If you want to draw a couple waves, that's typically what I have students do. Doing fantastic. Remember, if we don't have enough time to go through the entire presentation, you will get a copy of the presentation. So there'll be a link here at the end so that you'll get that. And then if you don't get it, you can always email me. I'll put my email in, and I can send you just a copy of the overall presentation itself. Okay, good job. So remember, it is moving to the right first. So it's moving in the positive direction first. So you're going to start at 0, and then you're going to move positive. This is fantastic. You're doing awesome. Love it. Just more sketching of these graphs. But this one definitely is a little bit different because it is horizontal. Excellent. All right, so we've got some people that are done. We've got some people that have just started kind of in between all of these. And so I'm going to show you a couple of solutions that people have. All right, here are a couple of solutions. Here's our first one. This one, we start a position at 0, and then we move positive, and then we go back to 0, we move negative, and back to 0. So we know that that one's position, we know acceleration is the inverse. We know that the velocity, if this is 0, there's a 0, and the bottom is 0, so we put a 0 there. We know that we have a positive velocity first from the slope of the position versus time graph, then a negative velocity, then a more negative velocity, and then a positive velocity again. So you'll see those as they go through. This person did exactly the same thing, so nice job. Here is the complete solution for this one. You'll notice that the top two look very similar because they are force and acceleration. And then the acceleration and position are inverse. And our velocity is here down on the bottom. Nice job. All right, so let's go back. So doing those horizontal springs, super easy. The vertical springs are a little bit more difficult. Here's the next thing that they might have you do with this. So they want you to sketch a free body diagram or a force diagram for the block as it goes through positions A, B, C, B, and A. So they're taking the block, they're raising it up to A, and then they let go. And when they let go, you're going to draw the forces on A. And then when it gets to B, draw the forces when it's at B. And then draw the forces when it gets down to the bottom at C. And remember, it's only moving up and down. So you really only need arrows that are in the direction of motion for this one. So there are no forces left or right here. We only have forces in the vertical. If we had forces left or right, it would be something like maybe there's air blowing on the block, and then it's going to oscillate, but it's going to make a circle, and it's going to be super complicated. So remember, we just want arrows pointing up and down for these. So good job. Seeing some good responses so far. So we're drawing free body diagrams or force diagrams, looking at the forces acting on the block when it's at position A, at position B, when it gets to C, and then when it comes back up and goes to B and then gets back up to A again. Seeing some good answers here. And so we just want the individual forces. For those of you that might be struggling, there's only 2 forces acting on the block. And so you should have 2 arrows on A, 2 arrows on B, 2 arrows on C, 2 on B, and 2 on A again. So Anna, you asked if anything would change with the potential energy graph. The potential energy graph would only change if you change the stretch or the spring constant. If you change the mass, would that make a difference? So remember, it's 1/2 kx squared is the potential energy in terms of just spring energy. If you add to that the potential energy due to gravity, then you would have to think about the mass. All right, very good. I'm seeing a lot of good ones here. A lot of good pictures. Excellent. All right, so let's just take a look at what some of you have done. So here's our first one. Here's our second one. We've got 2 arrows on each one. They're going through. Here we've got 2 arrows all the way across. Good. Kind of varying lengths. Excellent. There's another one looking good. It's another one. Somebody's putting their dots on. I love it. All right, so let's do this. Let's go ahead and take a look at what the solution is. And I think you're going to be blown away. And here's why. If you notice, these arrows on the bottom are all for the force of gravity. And I also put some extra letters on here so that you kind of know what the two things are that are acting on the block. So here we've got the force of gravity from the earth, and it's acting on the block. And it's the same all the way across, because remember, the block has a weight that does not change. So every single one of our arrows on the very bottom, you will notice, are exactly the same length. Now, when the spring is compressed up top, okay, when we take some slack out of it, it's not actually compressed to the point where it's going to put a tension force down. So instead, we've got a tension force in the spring. You could also have put just Fs, which is the spring force. But this is the force of tension on the spring, on the block from the spring. So you'll notice that it is very small, then it gets a little bit bigger at B, and then it's really big at C. And the key here is the mg force needs to be bigger than the spring force. Here they're equal, because remember, at this point, this is our equilibrium point. So if it stops bouncing up and down or bobbing up and down, then the two forces would be equal and opposite. This is also where it has the maximum velocity if it's moving. Then when we're at the bottom, it's got to be accelerating up, because at the bottom, when it stops, it's accelerating in the positive direction. So this is a difficult thing to do. So another one of those things that they love to try to put on the AP exam, not to trick you, but to check and see if you truly understand what's going on. Let's go ahead and take a look at this graph. So this one is just the same type of graph that we had done earlier. So we aren't going to actually do it. Instead, let's just take a look, make sure that this one makes sense. We're starting at position A. Remember, that's above the equilibrium, so it's up here. Then it gets to equilibrium at B, and then it goes to the bottom, or the negative position, here at C. So we said that our zero position is at B. Our velocity, you'll see, is here. Acceleration position are opposites, so they're inverse. And then our force follows along with that acceleration one. All right, cool. Now, this one is a question that you should be able to answer. So whenever we do simple harmonic motion problems, there's typically a force diagram or a force problem to do too. So this one is going to ask you a question, and it says, I have an ideal Hookean spring. The spring constant is 20 newtons per meter, and it's connected to a 0.5 kilogram block. The asterisk is the position of the spring when it's unstretched. So they want to know, it says, use your position B as your zero height for measurement of gravitational energy. They want to know, how far does the spring stretch when the 0.5 kilogram block is slowly lowered to position B? How far does the spring stretch when we start it at, when we hook the block up, and then we gently lower it down to position B? And so you don't need to worry about here where it says use position P as your zero height for measurement of gravitational energy. So we're not going to worry about that. But we do want to figure out, how far did it actually stretch? One thing that you might want to do is think about the force of the spring and use it. So I'm starting to see some people thinking about this just a little bit. One of the things that you might want to think about is, what is the force of gravity on the spring? And so we're looking for how far the spring will stretch when I slowly lower it from when I put it on right at the star position until it comes down. It's another one that's a little tricky here. So you do need to know the force on the block. And remember, the force on the block is just mg. We also know that force of the spring is K times X. We know K, and we're looking for X. So I'm seeing some people do some awesome free body diagrams. They're using some math here also to go through and do this. And by that, I mean, I'm going to show you what somebody's doing to kind of help. So this person started by saying the sum of the forces is equal to MA, which is perfect. Don't erase what you're doing. It was perfect. Oh, well, you were doing a great job. So they're going to go back. There we go. Good job. Excellent. Okay, so here's another one where they've done some of the forces. We know it's not moving here. And they went ahead and put in, and they found an answer of about 0.25. And that answer is actually very correct. So here's how I did it. I went through and just said, well, I know that the force that is pulling the spring down is 0.5 kilogram times the value for the acceleration due to gravity. And that is 9.8, or the gravitational field is how you can think about it. If you want to use 10, you could also do that. If you use 10, you do get 0.25. And then the spring constant is just 20 newtons per meter. So this one, it seems really complicated because they're talking about how they're slowly lowering the block from this position. But in the end, it's just a Hooke's law problem. And so that's what we'll see. All right, so there's a few more things here that they're going to talk about in terms of, they're going to pull it down, and they want you to figure out the elastic, the gravitational, and the kinetic energy of the system system at position A. We're going to skip through some of these. I'm just going to show you some answers here, and then we're going to go on and take a look at pendulums for just a second. So EE is the spring energy. So just another way of showing how spring energy is. Usually we would do US, and that's 1/2 kx squared. So they've taken 0.245. Remember, that's how far it was from the star down to the B. And then they stretched it an additional 0.1 meters. Because that is the total stretch. That's your X. You have to square it. Then we put in our K and do 1/2 of that. So hopefully you see when it comes down and it's at B, it is being stretched 0.245 meters. We're going to stretch it an additional 0.1 by applying an outside force on the system. When we do that, we have 1.19 joules of energy. The potential energy due to gravity when it's at A, remember 0 is our height here. And so when we pull it down, that's actually a negative 0.1 meter. And I get negative potential energy due to gravity, which is something that you can do. So if I say 0 is here, this is negative position. When I do mgh, that's the weight of the block times this. So that would be kind of what you're looking at. And then my kinetic energy here is 0. So if I add the two things together, you would see what the total energy is. We do the same thing at B, and you would get the values that you see here. And you'll notice that the total energy is not changed. When I get to here, I'm going to see that what the speed of that block is. And then for this last one, we're looking at the elastic, gravitational, and kinetic energy at position C. So we've got all of those again. This is just another one where we're looking at the mass and how the mass has changed, and the spring now is replaced with another spring that has a constant of 15.2 newtons per meter. So the period with this new mass is 0.66. They want to know how much mass do I have hanging on the spring. So I'm going to give you a little bit of time to work through this one. Notice it does say that it is at rest. It is at rest. And the mass is changed. And so the spring constant has also changed. They give you the period of the mass in the spring, and that is 0.66. So one thing that you might want to do is, I'm going to pull up the AP Physics 1 equation sheet, and we'll take a look at it. We just want to make sure we get the right equation for period. So I'm going to pull that up, and we'll take a look at that equation for period of a spring, and then that might help you a little bit on this problem. So here are the equations that are on the equation sheet. We're really looking for all of the ones that deal with simple harmonic motion. So we know we've got our position equation, and it is here. We want the period of a spring. So here is the period of a spring. It is Ts is equal to 2 pi times the square root of m over k. So that's the period of the spring. So we're going to use this equation. If this was a pendulum, we would have to do Tp is equal to 2 pi times the square root of L over G. All right, so there is our equation that we need. Ts is equal to 2 pi times the square root of m over k. And I see some people are already putting that in, which is fantastic. We want you to find what is the new mass. What is the new mass? So take your time. If you want to do that on a piece of paper, you can do that. And then just put your final answer in. If you want to show us your work, that would be absolutely fantastic. You could do that also. We typically see more questions about springs and spring energy in the free response than we do about pendulums. Although every once in a while we'll see a pendulum. But they've done a lot with springs and energy. A couple years ago in 2019, they had one that was pushing a ball or a block. And so you had to figure some things out about the spring and the energy, and then the speed of the ball and position of the ball and some other things. So seeing a lot of good answers here. You guys are doing great. Don't have anybody with a mass yet, but remember, a lot of times your final answer is not worth any points. It's all the work that you have to do. So doing the work is super important for this one. We are looking for mass. So the big thing that people do incorrectly on this one is they forget to square things. So you'll definitely want to make sure that you're squaring everything, including the 2 and the pi, if you need to do that. All right, so I'm seeing some good answers. I've got a 0.17. I see a 1.05 kilograms. I'm seeing another one that is 0.168. That's awesome. So looking good. All right, so for this one, I'm going to show you what it looks like. We know that T is equal to 2 pi times the square root of m over k. So all I did was I squared everything, and that got rid of my square root. So now I have T squared is equal to 4 pi squared times m over k. A lot of people will forget to square the 2 and square the pi. And if you do that, you're going to get a really different number. It'll be much bigger than what we have here. So then I just rearranged it for m. I multiplied both sides by k, divided both sides by 4 pi squared. And then I plugged all my numbers in. So 0.66 is my new period of the spring. 15.2 is my new spring constant. So the tendency sometimes is you'll get in a rush and you'll accidentally put in the 20. So we want that 15.2, and then on the bottom we have 4, because 2 squared is 4, times 3.14 squared. And if you do all your math, you should get what a few of you got, and that was 0.17 kilograms. All right, fantastic job, folks. You guys did an awesome job today. One of the things that we're going to do is we'd love for you to join us in Discord. If you have more questions and things, Brianna, our wonderful TA, will do this. And so that would be really good. I'm going to go ahead and I'm going to call this one 5-able, and then this one is 41021, and this one is SHM. So I'm going to save it, and I'm going to put the link to the takeaways in the chat, and then we'll answer Spondan's question here too. So in the chat, you're going to see a link. If you go to that link, it will tell you that it's processing. Once it's done, it will pull up automatically a Google Doc that will have everything that was in this. And Spondan says, what would the graph of a total potential energy of a vertical spring mass oscillator look like? So that's a great question. And I think the best way to answer that one is to use this little CAMI program here so we can draw some things. And it depends on where you're putting your 0 point. So if I have my spring and then I have my box, and let's say that my 0 point is up here, then all of my gravitational energy is going to be negative. My spring energy will be positive. So this will always be positive. So the interesting thing that'll happen is if you're looking at the total potential energy, so this is both UG plus S. If I pull it down, and let's say that I don't have much stretch and I don't have a very big spring constant, then it's, well, if I don't have a big spring constant, it's going to come down pretty far. But instead of this one kind of doing, you know, the camel humps on top of the line, we're going to get something that might be a little bit different. And so you'd actually have to go through and do the math in order to kind of figure out what it is. So if your UG is negative, but that's a bigger negative than what your spring energy is going to be, then you'll definitely have a graph that will not just look like what we had before, where it was just everything was on top. So that is the one thing. Remember, the kinetic energy will always be positive, so you'll kind of see that. All right, everybody. Hey, head on over to Discord, and you can kind of take a look at some things there. Otherwise, we are done for tonight. I will see you next week for sure, and we will go through rotational motion. All right, everybody. Hey, have a great night. And like I said, you can go on over and do that. Yeah, no, that one wouldn't be a simple sine wave anymore. So if that one was potential energy, so your energies aren't going to give you a sine wave, and they're not going to give you a cosine either. Your energies are always going to be that modified wave. Kind of looks like a camel hump as it goes all the way across. All right. Hey, thanks everybody for coming out, and we will see you